Okay, welcome back to our Calculus 3 class notes. Professor Sebastian back here, and we're on about the middle of page 57. We're looking at properties of the directional derivative. So we just got done learning about the directional derivative, and notice that the derivative of f in the direction of u is defined as gradient of f dotted with u. Now, if you remember the definition of the dot product, that's the magnitude of the one vector times the magnitude of the other vector times the cosine of the angle in between them, call it theta. But the magnitude of a unit vector is obviously 1. So the properties of the directional derivative are going to be based off the fact that the dot product here, or the derivative of f in the direction of u, is really the magnitude of the gradient vector times the cosine of the angle that's between the two vectors, all right, between the gradient vector and the direction that the derivative is in. So the first property is the function f increases most rapidly when the cosine of theta is 1, right? That's the largest that the cosine of theta can be, which means that theta is equal to 0. So u is the direction of the gradient of f. So that is, at each point P in its domain, f increases most rapidly in the direction of the gradient vector, the gradient of f at that point P. The derivative in this direction is, the derivative of f in the direction of u is the gradient of f, the magnitude of the gradient of f, times the cosine of 0. So it's just the magnitude of the gradient of f. Similarly, f decreases most rapidly in the direction of the opposite of gradient f. The derivative in this direction is, derivative of f in the direction of u is the gradient of f. So times the cosine of pi, we have an angle of 180 degrees between them. So that means we're going the opposite direction of u. It's minus magnitude of gradient f. You can think of this like if you're standing on the side of a hill, and you could walk along the side of the hill, and that would be not the most steepest path to take, right? Or you could look up at the top of the hill, and you could just start walking straight up to the top. That would be the steepest path to take. So that would be the gradient of f. Or you could look down, down away from the top of the hill, and directly away from the steepest path up would be the steepest path down, right? So that's what we mean by decreasing most rapidly. It's in 180 degree direction from where it increases most rapidly. Any direction u that is orthogonal to a gradient of f not equal to 0, of course, is a direction of zero change. That's like walking along the side of the hill, but you're not going up or you're going down, right? So u is orthogonal to the gradient of f there. So that's when theta equals pi over 2, and that means that the derivative of f in the direction of u in that direction is 0. There is no change. Again, think of that as walking along the side of a hill. So, as an example, let's find the directions in which f of xy equals x squared over 2 plus y squared over 2. So we have a right side up parabola centered with the apex here down at the origin. We want to find the directions in which f increases most rapidly at the point 1, 1. So here's the point 1, 1, which gives us the point 1, 1, 1 on the paraboloid. And which direction it decreases most rapidly at that point. And what are the directions of zero change? So we just went over that. F increases most rapidly in the direction of the gradient vector. So the gradient of this vector, the gradient of this function is xi plus yj, right? So it's just the vector xy. So at 1, 1, that's the vector 1, 1. So that increases in the direction of 1, 1. So if I were coming from the origin out in the direction of 1, 1 would be this way. So this is like coming at a 45 degree angle out towards us, right? So this would be coming out this way. And that's the direction of increasing most rapidly. So then if you look at direction it decreases most rapidly, that's the opposite of that direction. Okay? So now again, if we're going to talk about direction, we want to think of these as unit vectors. Okay, so to get at a unit vector, you just divide it by its length. That's all there is to it. Whenever you say the word direction, you really want to think the direction as a unit vector. Okay, so directions of zero change in f are directions orthogonal to the gradient of f. So you just have to imagine what's orthogonal to these. It would be where you switch the sign on one of them. Okay, so it would be minus 1 over root 2i plus 1 over root 2j, or minus n, which is 1 over root 2i minus 1 over root 2j.